Our next speaker, Dr. Danielle Williams, is a Mellon postdoctoral fellow in modeling interdisciplinary inquiry at the Washington University in St. Louis. Dr. Williams explores the fascinating intersection between philosophy, neuroscience, and artificial intelligence. Her interdisciplinary research delves into how we perceive and represent temporal structures in our daily activities, and how do we process the spatial relationships between our body and the external environment. Please join me in extending a warm welcome to Dr. Williams.
Thank you. Can you hear me? Okay, great. It's nice to be here. So today I'm going to talk to you about why we think of the brain as a computer, kind of historical picture of how we ended up just taking the brain as a computer. I think it's often taken for granted in different contexts that the brain performs computations without considering what it is about the brain that makes it a computational system in the first place. So some questions philosophers have been working on. Like me, I'm a philosopher by trade, but doing interdisciplinary work with neuroscience and artificial intelligence, in particular, thinking about how the computational modeling practices in the cognitive sciences relate to physical mechanisms in the brain, or what these kinds of models can tell us about neural processes. And so some questions that philosophers thinking about this topic are asking include, well, what's the difference between systems that perform computations and systems that don't? And what does it mean for some physical system in the world, such as the brain, to implement a kind of computational structure, like a classic digital Turing machine style computational structure, or some other kind? And also, which computations does the system perform? So what kind of semantic interpretation can we give to the computational process? And philosophers working in this area are asking these questions, and it's a metaphysical question about how we can know these things in the world. And so these are important foundational questions about the nature of physical computation, answers which are meant to help us understand whether the brain literally does perform the computations ascribed to them through our computational modeling practices, and if so, what makes it the case that it does perform these computations? Well, rather than answering any of those questions for you, instead I'm just going to give you the historical context that gave rise to thinking of the brain as a computer in the first place, and how this kind of paradigm came to be. And the goal of giving this historical picture is to help motivate maybe an intuition, or acknowledge the reason why we should answer these foundational questions about physical computation in the first place. In other words, it's not just a given fact about the world that the brain performs computations. In order to know that, we need an additional account, an additional metaphysical theory. So I'm going to start with the cybernetics movement. So the cybernetics movement took place starting in the 1940s, around the 1940s, and it's mostly gone out of fashion, although it has seen a resurgence in the 90s and early 2000s. So it's come back in some ways. But in the late 40s and the early 50s, a series of conferences took place called the Macy Conferences. This is a photo here from their last meeting, I believe. And it features some familiar faces that might ring familiar for some in the audience, such as Claude Shannon, who gave us this information theory, and then Warren McCulloch, who together with Walter Pitts gave us this logical neuron picture. So here are some quotes on the right-hand side from some of those in attendance during these Macy conferences describing the movement. So what is cybernetics? Here's some answers. So in this green font at the very top, that cybernetics is the science of control and communication in the animal and the machine. And this comes from Norbert Wiener, who's the founder of one of the founding people of cybernetics. In the beige text, which I believe is right underneath it. So in this beige text, we have a quote from Warren McCulloch, who's describing the cybernetics movement. And he says, "It's an experimental epistemology concerned with the generation of knowledge through communication within an observer and between observers and environments." In teal, in this teal, we have another quote here, and this comes from Jean Paget, who's that cognitive development psychologist who thought about theories in early childhood development famously. He says, "Cybernetics is the endeavor to model the processes of cognitive adaptation in the human mind." We have some other quotes. "It's a science of effective organization. Cybernetics focuses on form and patterns. It's the art of manipulating defensible metaphors, showing how they may be constructed and what can be inferred as a result of their construction." And so the main purpose, according to many of these people, of these meetings was to set the foundations for a general science of the workings of the human mind. How can we think about the complexity of the mind using scientific tools? So here are two very popular books, foundational books. If you're interested in cybernetics, I recommend reading them. I'm not going to tell you that you will like it, but you can read them. Ashby's book is a very nice way of thinking about how you might go ahead and kind of mechanize behavior. So what's interesting about cybernetics is that it takes an engineering perspective towards this science. So it's an engineering-oriented stance towards thinking about cognition or the mind. And the idea is that everything can be described as a system broken down into black box style components with inputs and outputs, and understood using the ideas of information, flow, noise, feedback, stability. This description, I should get a pointer. This description here, you can start to see why Claude Shannon was involved and Walter McCulloch and people of that nature. So cybernetics can be roughly understood as the origin for two related disciplines: artificial intelligence on the one hand, and then this exploration of human intelligence on the other, or what we might call cognitive science. So they took their views to be relevant to these two contexts, where in artificial intelligence, we could design technology. We can use this engineering kind of technique to build things like robots, automata, and computers. And based on the mechanisms in these kinds of systems, we can start to understand things about human intelligence. So there's this relation here. And this is the idea that if we can build it, we can understand it. So this quote up here, this Latin quote up here, it means truth is itself something made. So if we can build it, we can understand it, is the idea. And this is that engineering perspective that's kind of motivating the cybernetics movement. So you can see this tight connection already from the start between artificial intelligence and cognitive science, and thinking about computers and artificial intelligence and how that can help us understand our own cognition. But I think an interesting point here for cybernetics is that they didn't take their mechanical view to be realist. And I'm using this realist term in kind of a philosophical sense, where the technology that they built to understand human intelligence was never meant to be a representation of literally the mechanisms that produce human intelligence. It's very much built on this metaphor that we can use this kind of technology to facilitate understanding, but we shouldn't take that technology to be literally what that physical system is. So cybernetics rejects the belief that scientific descriptions and explanations should and indeed can approximate the structure of a kind of objective reality or a mind-independent reality. a reality independent of our own perspective, that exists independent of the scientist building that model. So I think this is a really important part of cybernetics here, is that they're really thinking in terms of a metaphor, and you can see that in some of these quotes here. So the art of manipulating defensible metaphors. So let's talk a little bit about the work of the people that were participants in this movement. So some of those in attendance at the Macy conferences and helped to establish the cybernetics movements are some of the same people who helped to influence early neuroscience and cognitive science. So here's a photo of Claude Shannon, and in the top left is just the front page of his dissertation. And then on the right is a photo of that front page of his very famous paper where he proposed his information theory, or where we get Shannon information from. So Claude Shannon, in his dissertation here in 1940, used Boolean algebra to establish the theoretical underpinnings of digital circuits, and there later developed the foundations of information theory here. So his mathematical theory of communication specified a measure of the efficiency of communication using a system called entropy. So if you're familiar with his work, that might make sense. If not, that's okay too. But these ideas are applied across contexts, including helping to understand information processing in physical systems, including the brain, if we think of the brain as an information processing kind of system. And also here, this might sound familiar, this Boolean way of thinking kind of sounds a lot like digital computation or early ways of thinking about it. So another participant here is Warren McCulloch on the left. And Warren McCulloch, along later with Walter Pitts, provided a way to describe brain functions in abstract terms, meaning using abstracta or mathematics, and showed that simple elements connected in an artificial neural network could have immense computational power. So we get this logical neuron here, and this is happening right alongside the cybernetics movement. And so this paper, this is that Warren and McCulloch paper, it's quite famous now, but it wasn't initially when it was proposed. It received little attention until it was applied later by John von Neumann and Norbert Wiener. The McCulloch and Pitts neuron was described using a language of logic, a perfect fit for cybernetics, and also thinking about the brain computationally. So when you have John von Neumann, who's starting to think about this analogy between mental processes and the brain, this computational picture here, Warren and McCulloch's work on the logical neuron gives you a very good entry point into understanding how the brain might perform computations. And it was also this book that I warned you about earlier also draws upon this work. So one thing, though, to keep in mind, even though John von Neumann is the founder, or like the father of building physical digital computers, sometimes thought of that way, in the final chapter of this book, which is his final book towards the end of his life, he challenges this analogy between the brain and the computer. And he says the only way the analogy works between the brain and the computer is if the brain is highly simplified and idealized. So even if the brain, drawing from McCulloch and Pitts, has this kind of prima facie digital character, it looks very much something like a digital computer with this all or none firing, this kind of Boolean logic. The only way that this analogy holds is if you think about the neuron in an extremely simplified and fairly distorted way. Once you look at how actual neurons work, this analogy doesn't hold up anymore. And this is a really, I think, important insight to keep in mind here, because John von Neumann is working within this cybernetics paradigm in a lot of ways, and so he's maintaining this analogical picture. He's not saying the brain is a computer. He's saying something like, we can use computers to understand how brains work. And McCulloch and Pitts give us a nice way to think about it. So something interesting starts to happen, though, in 1958 in particular. In an effort to better understand the application of digital computers, this new kind of technology where digital computers are being built and made more available for use in different contexts, thinking about how digital computers could be useful within the social sciences, and in particular at the time within psychology, this company called the RAND Corporation, who was engaged with different contracts with the military and the police and fire, and thinking about the application of technology across different social contexts, they put together a summer training institute to gauge the technology's application within scientific contexts. So you see a meeting take place in 1958 where they're like, how do we get this cool technology into science? And this is where you start to see this start to blur. And we get a blur between the technology and human intelligence. And we start to see this kind of connection happen, where rather than an analogy, or if we build it, we can understand it, but it's not literally the thing, you start to see this kind of, well, maybe the brain is a computer, and so computers can tell us literally about the brain. So some familiar people, if you're familiar with a little bit of the history of cognitive science and how it relates to artificial intelligence, two people who were involved in this meeting were Herbert Simon and Alan Newell. And so out of these activities, there grew a strong consensus in the group that computer simulation techniques do indeed have a promising future in psychology, both in the area of higher order mental processes, where most of the work has been done to date, and in areas of more traditional psychological activities such as concept formation, perception, and memorizing. So we can use computers in psychology to understand both higher order thought and these lower level processing systems. So let's look at just briefly at the end of this meeting hosted by the RAND Corporation, who has an interest in kind of moving this technology into other contexts, what are the conclusions that they reached at the end here? So I'm just going to do the thing where I read the slide to you. So they said simulation techniques represent a significant new tool for psychological and other social science research. The next important objective is to make the tool available as a normal part of graduate training opportunities at the major graduate training centers in the social sciences. We need to get this technology out, and we need to get psychology using it. Computing facilities of at least minimum adequacy are now to be found at most campuses with large graduate programs. So let's get, areas where people can use it. So they're talking about how some steps have already been taken to acquaint computer center staffs with information processing languages. That might be a typo. Newell and Simon have been active in summer training programs. So we're seeing really this technology move in as a tool in psychology. They're preparing a manual using information processing languages with the IBM 650, an old kind of computer, and the IBM 704. The manual, which is being prepared by the RAND Carnegie Group, will be distributed to computer centers and to behavioral scientists probably in early 1959. And if you're familiar with a little bit of the story that gets told about how computational kind of theories about the mind come into play in cognitive science, it's meant to typically follow behaviorism. We want to have some way to model the mediating processes between the environmental stimuli and the behavioral output. So how do we do that? Well, it looks like computation is a really helpful tool for doing something like that. So you can kind of see this side of it following that same sort of story. So the participants in the Institute will constitute a nucleus of faculty familiar with these techniques across campuses and universities. So hopefully, I think the point is taken right here. There was like a real plan to get these computers into psychology and to get them using this kind of technology. So I just want to really push here that here's where we start to see a kind of shift out of the cybernetics analogical way of thinking of things and kind of bringing together computation in the brain in psychology and in training. Okay, so right around that time, this is 1960, we end up with this book, Plans and the Structure of Behavior. One of the authors is George Miller. You can see the top author on that book. George Miller might sound familiar if you're familiar with the 7 plus or minus 2 rule that we can hold only 7 plus or minus 2 bits of information in memory, and then we use this thing called chunking, right? Does this sound familiar maybe? So that's that, and that theory relies heavily on this idea of how digital computation works, and from this book, there's these quotes here. So we slowly became convinced that Boulding and cognitive psychologists generally had not told a complete story. We thought we knew a part that was missing. Although we could accept in spirit, if not detail, the argument that cognitive theorists made, it left an organism more in the role of a spectator than of, and it goes on. But the important thing here is that they say, well, it seems to us that a plan is needed in order to exploit an image, and the notion of a plan that guides behavior is, again, not entirely accidentally quite similar to the notion of a program that guides an electronic computer. In order to discover how to get the image into motion, therefore, we reviewed once more the cybernetic literature on the analogies between brains and computers, between minds and programs. So they're calling upon this picture in cybernetics where we're using this kind of technology. Remember on the left-hand side, we build computers and robots to understand human intelligence, thinking of the image that I had on a slide before. But they're taking it a step further. And so in this book, they rely heavily on work from Alan Newell and Herbert Simon, and also J.C. Shaw. And an interesting thing about J.C. Shaw is that he worked for the Rand Corporation. So you have this connection here. And they give us this elements of a theory of human problem solving in terms of a digital computer. So we're really seeing this connection happen. Okay, so then what happened in the 1960s in cognitive science? If you're familiar at all with the Turing machine, which right here, it comes from Alan Turing's 1936 paper, but starts to gain a lot of traction in the 1960s because this is a mathematical theory of digital computation. It's a way that we can give a kind of formal, abstract description of what physical computers do. And so it enters cognitive science as a really nice way to describe mental processes without having to say anything about the physical realizers or directly relate mental processes to, say, neurons in the brain or something like that. Let me catch myself up on my notes. Okay. So Alan Turing's work is really making an impact now in cognitive science in the 1960s, right around when these computers are being pushed into psychology labs and starting to have Newell and Simon's work on thinking about the brain as a computer. Am I okay on time? Yes. Okay. So we have this kind of picture coming in as well. And then on the philosophical side of things, we have this is the same exact paper. It ends up being published twice in different forums. So these are the same paper, just once in 1967 and then once again in 1975. And this is a picture of Hilary Putnam when he was quite young, I think, a philosopher who contributed a lot to philosophy across many different areas, and in particular gives us this picture here and uses the concept of a Turing machine, this kind of picture, uses the concept of a Turing machine to describe mental processes, setting in motion both this kind of functionalist paradigm, which is often told to replace behaviorism in some ways, and it still kind of underpins a lot of the methodology in the cognitive sciences, and underpins this computationalism thesis that the mind is a computer. That in particular, the functional organization of the mind is computational. So we get this kind of picture entering the world in philosophy. So philosophy is now using these tools to understand mental processes as well. So we see a kind of parallel development in the idea that the brain can be understood in computational terms across several disciplines, including computer science. Alan Turing was a computer scientist and mathematician. In engineering, in psychology, and philosophy, we get this picture really starting to take shape. And in 1976, things get pushed even further when Newell and Simon, who are some familiar characters, create this famous paper that argues for what is called the physical symbol system hypothesis, which claims that computers can demonstrate human intelligence, and then human minds are also physical symbol systems. So a physical symbol system, such as a digital computer, for example, has the necessary and sufficient means for intelligent action. Is anyone familiar with this paper? Is this new? A couple of people? If you take like a philosophy of AI course, you'll probably be forced to read this. But at the same time, they're saying, well, the symbolic behavior of man, or humans, arise because they have the characteristics of a physical symbol system. Digital computers are physical symbol systems, and so are human minds. So we get this tight connection here, right? This blending between ideas in artificial intelligence and now in the cognitive sciences. And I think it's interesting. I just have this slide here. I'm not going to try to argue too strongly for this, but I'll just drop it here and maybe you can think about it too, is that Warren McCulloch and Walter Pitts' picture here about the logical neuron often and sometimes gets called the first digital model of the mind, so the first computational theory of mind. But you might wonder, were they really giving a computational theory of mind and saying literally that the brain is a computer if they were working within the cybernetics movement? So it's kind of been, the lines or the aims of cybernetics have been blurred so much over this historical path that, I don't know, we might wonder whether they really were giving a computational theory of mind in the sense that we understand it now. Or were they doing something more like what the cybernetics movement did and just kind of giving us an analogical picture? I don't know. Maybe you think one or the other. Okay. So more things are getting pushed forward, right? In the 80s, we have Jerry Fodor's famous language of thought that relies on this computational picture of mind. He does some additional things and pairs it with some representational ideas, but nonetheless, the foundation of Jerry Fodor's view here, which is highly influential to this day in cognitive science and in philosophy, is using this idea and relying on notions of computation in order to understand mental processes. And we also have this other view in 1987 that comes from Rumelhart and McClellan. So we have psychologists now proposing computational theories. This is in terms of neural networks. This is classic digital computation. There's a whole literature about this, but the point here is just to see that we have computational pictures of mental processes coming out. And then in 1994, we have a more neuroscience-oriented kind of picture. I just plucked this book from Patricia Churchland, who is like a neurophilosopher, and then Terence Sidnowski, who is a neuroscientist. And so we see across disciplines, philosophy, psychology, neuroscience have really picked up this way of understanding the mind as a literal computing system. Okay. So what I'm hoping here is that we can see this transition from analogical reasoning and psychology, where we can use one to understand the other and maybe vice versa, but they're an analogy. So cybernetics early on was just saying we can use technology, we can do engineering-oriented science without taking literally the claims made in cybernetics, has kind of morphed into this picture where now we talk about the brain as being a computer, and across contexts you might say things like, well, the brain performs this computation or that computation, or we know that, when the brain computes this or computes that. Well, I don't think always we're just talking about that metaphorically, right? It literally is just this assumption that the brain performs computations. But there are questions. What is it about the brain that makes it a physical computing system? And what's the difference between computing systems and non-computing systems? And these questions are never answered in this transition. Now, philosophers are working on these kinds of questions, but it's not always clear to me across various contexts that people are aware that these questions are even there to be answered. And so I'm just hoping that kind of talking through the history of how this happens and seeing this trajectory, maybe to others who are thinking about physical systems in the world as being computational, might stop for a second and ask, well, just because we can model it using this incredible tool, does that then mean that we're warranted in saying that system literally does perform those computations ascribed to it? So it's just a pause. Think maybe we need a theory to understand whether that system literally is the kind of physical system that performs computations in the first place. And that's it. That's all I have. Yeah.
Thank you, Dr. Williams, for your fascinating lecture. We'll now open another Q&A session. So if you have a question, please raise your hand and we'll make your way up to you.
Very nice talk, Danielle, as usual.
Thanks.
One point that has always kind of struck me, and you brought it home very well. The philosophers who were working on bringing about this picture of the mind as a computer, the mind, the brain computing, really did apply real science to the state-of-the-art science. Putnam, Fodor, and the like were really applying what was going on in cognitive science at the time to make their philosophical points. Mm-hmm. It's interesting that the so-called mind-brain identity theorists of the 60s were doing nothing of the sort. They were talking zero neuroscience, C fibers firing, and it's really interesting that the line of thinking in philosophy that developed the brain as computer was really bringing state-of-the-art science into the picture from the beginning, and it wasn't for another 20 years before those of us who think the brain is, a chemical stew, we're really bringing science into the real neuroscience into the picture.
Yeah, I agree. These, Jerry Fodor's, he's one of the founders of cognitive science, and he's really, when he puts forth his theory of, his language of thought, he says this is an empirical hypothesis, right. And it seems like we have a lot of reason to think that this is true, and the sciences will tell us whether it is or not. But the early identity theorists were doing this strange thing, I think, where they were trying to think about how terms in a language refer. Exactly. And, you know, I'm not even sure that Putnam's criticism of what the identity theorists were doing really holds water. He might have done them dirty in some ways, I think. But their project, in some respects, wasn't even about what neuroscience was doing. It was, how do our terms refer? And you get a really strange kind of theory, a really counterintuitive way of thinking about reduction when you start to apply it to the sciences. So. Yeah, and I will just point out that I've talked about philosophies picking up this picture, and I think, John, that's a really great point, that these philosophers are really thinking in terms of what scientists are doing, because when I talk about, there are these questions, what is it for a physical system to implement a computation? Well, Hilary Putnam gives us one of our earliest theories of what that is. And so he's not just hey, the brain is a Turing machine, take that. He's and here's how we understand it through this kind of mapping. So philosophers, this is what I mean, it kind of starts here in philosophy, thinking about how do we relate this abstract, formal mathematical description to the physical system. And I think that's just to your point, that they are engaging with how science is done, but they're also trying to tackle these additional metaphysical questions. What is it to instantiate some kind of mathematical formalism? And yeah. Nice.
Thank you for your talk. One thing that struck me a little bit is, maybe it's a follow-up, that you did not mention British cybernetics. And I think the British cybernetics had actually interesting influence on American philosophy of mind. Because Gilbert Ryle's PhD student, Dan Dennett, actually was heavily influenced by J.Z. Young and his neuroscience, but as well as by Donald McKay and his information processing and cybernetics. So I think in some ways British cybernetics was then brought to the US via Dennett, who remained in some way influenced by that movement and was bringing those insights. So what do you think that is also something that had some other insights, or I mean, I think this is an interesting historical counterpoint.
Yeah, I think so. I'm not sure if I said it, but I thought whenever you try to give the history of something, some things are in, some things are out. And of course I cannot do justice, but my aim here is really just to try and tell some version of the story that really gets at how this happened, how we end up now just kind of saying this without reflection. I think that the brain is a computer. I think it, and I won't say everybody does, but if my experience is worth anything, I think it happens quite a bit in the brain sciences. But I think it's worth thinking of this story with that part in mind as well. And so I will just admit that this is kind of an early. I've spent a lot of time thinking about the history of artificial intelligence and that trajectory. And while it's related to cognitive science, it has important differences. And so this you can see as an early kind of start to thinking about the trajectory of the other side of how cybernetics influence cognitive science, and there's more work to be done. So yeah, and definitely more work thinking about how cybernetics in different contexts has influenced cognitive science and the differences between them. So yeah, I will just say I have more work to do, and so I appreciate. Yeah, I also had 30 minutes. 30 minutes. But thank you. Yeah, I appreciate that. I think there's definitely more work to do, and I think whatever story that I try to tell in this direction may in some sense never do justice to really the intricacies of how this kind of thing or this picture developed. But yeah, thank you.
Okay, do we have any other questions?
Okay, thank you for the talk. Please correct me. I'm here. Yeah, here.
Oh, thanks.
Yeah, please correct me if my line of reasoning will be wrong, but if I think about computation, I think about information processing. And information processing itself can be understood as some kind of compression, generalization, abstraction, integration, different terms that I can conceptualize this. And my question is, I'm curious about your definition of the information itself. What is information in your opinion?
You want my information there? I think first I'll just say that I wouldn't take computation just to be information processing. I don't think necessarily every system that processes information is going to be a computing system. There are important differences. There's been some work on this. If you're familiar with Gualtiero Piccinini's work, he has a paper kind of drawing the distinction between information processing and computation and separating the two. But I think, what is information? This is kind of a hard thing to think about, I think, especially, and hopefully I'm going to address or give you the answer you want from me when I say the things I'm about to say. But I think about physical computation, in particular thinking about computation in the brain and what kind of information would be involved in the kinds of, if the brain computes, the kinds of computational processes in the brain. I think it's hard to understand because the difference between computational artifacts and the brain, if it is a computer, is that the content in these computational artifacts, we ascribe to it, we interpret. It's based on, the user or the context or whatever, how we interpret those symbols. But the brain seems to be something different. Whatever information is there is there naturally, so to speak. It's not, it doesn't get its meaning in virtue of some observer interpreting it. And I think, there's some differences in the kind of information or how the information is ascribed to the system. And I just kind of say that knowing I have a lot more thinking to do when it comes to trying to understand that. But I think that difference is worth thinking about if we're going to think about what information is within like a computational brain per se. And I don't know that some of the notions of information that come out of like engineering or even Claude Shannon's work is going to tell us anything about the nature of information. It's a theory of communication, right, in terms of degradation of, when it starts at the original source and gets to the receiver, but that doesn't tell us what information is. And so I've struggled with this because Shannon information is often invoked to maybe I'm just talking a lot right now. It's often invoked to say that, to say, oh, what kind of information is it? It's Shannon information. And my thought is, that's very strange. Because I don't think Shannon ever says what the nature of information is or like what it is. He's just giving us a theory of communication. The paper was written for Bell Laboratories. This is a telephone company, right? So, yeah, I don't know. I just spoke a little bit. I don't know if that kind of addresses, at least I've given you maybe my thoughts, but I can't tell you what information is. Some philosophers think about it. Maybe it's, there's some work on what's natural information, non-natural information, and maybe you can pair that. I have some philosophers, I'll mention Piccinini's work again, has tried to pair these things together to say something more substantial about information in computation, but I don't know if it is satisfying. You can.
Okay, here's another view of it. Sorry, thank you. Here's another view of it. Information, especially in the Shannon sense, is a piece of mathematical abstraction. It has no more existence in the real world than does the number 3.
Yeah. Yeah. So I think you're just saying the problem exists there too. So how do we okay, so I'm saying
Nothing in the real world processes, that's just a piece
Yeah, but don't we want to know how it's possible for physical systems to instantiate abstract mathematics? You don't. I mean, I'll show my cards a bit. I am highly doubtful of anything like a relation between abstracta and the physical world, or whether anything like that can be carried out, especially when it comes to the brain. And I think that that's really what we care about. Other systems, these things we build in the world, of course we understand how they work. We built them. What we really want to know is, what is information in the brain? What is computation in the brain? And those are the hard questions.
Okay, so I want to ask, does the computational theory of mind address the qualia problem? Or is it more so about mental processes and thinking and not the consciousness itself?
I think there's two ways you can go within the computationalism thesis. You might want to just think about it without thinking about the phenomenological experience that accompanies thought, but you might think, well, you can't do one without the other. So I think there's an interesting paper that talks about how if you give this kind of computational picture, I'm trying to think of what it's called. But it's like if you give like your classic computationalism picture in terms of like, well, how do you know the brain implements this story? Well, there's kind of like a mirroring relation between the computational description and the physical world. And that if you give a story like that, you end up with kind of like, and then you want to explain consciousness, you just get this, okay, then there's this additional structure, and you kind of get like superfluous structures, and now it's like, well, I don't know if it's going to work if computationalism or this computational picture is going to work to explain the phenomenal aspects of it. So I know there's been work on that. So I think it just depends on like who you are, whether you just want to think about computation without thinking about how the phenomenal experience goes along with the computational process in the brain or the thoughts. But you might be interested in, I run from phenomenal consciousness at like every chance I get. But does that kind of address? So you can be a computation. Yeah, and so you might just be interested in thinking, like Jerry Fodor was interested in giving thoughts, and I don't think he's addressing the experiential aspect of it, at least not explicitly. But you might say, well, you can't do one without the other, and so you might be interested in, okay, how do we understand this part?
We've got just enough time for one last question.
Hi. Yes, so with all the advances in artificial intelligence, what sets human intelligence apart?
Okay. I think these questions are so good. You want the big answers. Okay, if you ask me what sets human intelligence apart from artificial intelligence, what if I give you a different kind of answer? And I say, what sets the kinds of computational systems or models used in artificial intelligence, like, say, deep neural networks or these kinds of convolutional neural networks which perform these really cool tasks like image recognition or language tasks. What makes those different from the actual brain? And how I would answer that is that they are, maybe we can channel John von Neumann and say the only way those represent anything like what the brain is doing is if we simplify the brain so much that it's no longer recognized as what the brain is doing in any way. So it's so simplified and highly idealized and distorted that the difference ends up being that even if we call it an artificial neural network, it looks nothing like the brain. It doesn't perform that process in any respects, like how the brain performs it. And so then I say, I don't know what the difference is, the question you asked me, but I think whether those models have import into the cognitive sciences to tell us anything true about the brain, I don't think they can do anything like that, about how the brain works or how the brain produces, transforms information. Does that make sense? I think I wrote a paper on this.
Okay, I actually think that this was a great question to end this Q&A.
I don't know how to answer.
So we are going to take a 15-minute break now. Please, let's thank Dr. Daniel for the real presentation.